Hi, my name is Stefan Herbold and I welcome you to this video about our paper Smoke Testing for Machine Learning, Simple Tests to Discover Severe Defects, which we published in the journal Empirical Software Engineering. This is joint work with Tobias Haar. Software for machine learning is becoming quite common. With artificial intelligence solutions being considered for more and more problems, libraries for general-purpose machine learning like scikit-learn or Weka, for deep learning like TensorFlow, for working with big data like Apache Spark or Apache Mahout, or statistical packages which include machine learning options like Stata, R, or SPSS, or even MATLAB, which was initially designed for working with matrices, include all components to support machine learning. There are also many modern applications already built around machine learning. Fraud detection runs credit card transactions through learned systems to identify possibly fraudulent transactions. With object recognitions, we can analyze pictures or videos to detect which kinds of objects are in them. Banks use credit scoring mechanisms based on historic data that then learn which customers have a good or bad credit rating. Or many different techniques, especially from computer vision, but also from reinforcement learning, are combined to achieve autonomous driving. When we speak of the testing of machine learning, we usually mean the following. We have some training data, which we throw into some learning algorithms like a decision tree or a deep neural network, and then we get the model. Later, we use some test data, which we feed into our model to test how it's working and evaluate it with some machine learning metrics like accuracy, precision, or recall. This is not what our work is about. Instead, we're considering a complex test process as is common in software testing, especially when it comes to larger systems. So based on a clear specification, it's about validating the correctness of the system, how robust it behaves in different circumstances, how the system deals with exception scenarios, if all equivalence classes are supported as expected, if we achieve a desired test coverage, or whether the system also works at its boundaries. Unfortunately, this is still a mostly unsolved problem. So there is no test book like Testing Machine Learning Software for Dummies. We're looking at a small part of software testing here in greater detail, and that is smoke testing. The ISTQB defines smoke testing as follows: a test suite that covers the main functionality of a component or system to determine whether it works properly before planned testing begins. So it's about basic functionality. Our simple interpretation for the remainder of this video is it means that the most crucial functions just don't easily crash. So we have to ask ourselves, what are the most crucial functions for machine learning? This is what we've seen before. We have our training pipeline and we have our testing pipeline. And we want neither of them to fail. So one crucial function is the training and the model fitting. And another crucial function is that predictions work as expected, both without crashing anything. So we have a very simple test oracle. If our software crashes, our test failed. Then we wondered, how can we derive our smoke test suite? And we wanted to reuse things from the normal software testing literature. And one of the basic techniques is equivalence classes. And with equivalence classes, you basically partition your input space and identify, for these inputs, my software doesn't work, for these, it should work, and maybe for these others, it won't work. When you consider this for machine learning, well, most machine learning algorithms can work with more or less any numeric data, if you exclude invalid values like not a number or infinities. Additionally, most machine learning algorithms can work directly or indirectly with categorical data. Well, obviously there should only be valid categories in there, so the data should be valid, but as long as it's valid categorical data, it's also supported by machine learning algorithms. And most algorithms actually support the combination of both. So in the end, machine learning works with more or less all data, which is kind of annoying when we want to define equivalence classes, because it means we basically don't have big invalid equivalence classes like as they only contain here it's not a number or an infinity or something like that. So we were wondering how can we maybe still derive test cases here. So we looked at boundary value analysis. With boundary value analysis, you look to the boundaries of equivalence classes and then try to test there, because that's where things often go wrong, like one-off errors. However, if we more or less support all data, it also means we more or less don't have boundaries. So for example, yes, we could test the largest or smallest possible floating point values. Okay, but that's more or less it. So this doesn't bring us very far. So again, it wasn't a suitable solution. But then we went one step further. We then considered, what are corner cases? So maybe we can use corner cases as boundaries. So no real equivalence class because everything should be working, but instead we use that machine learning works based on probability distributions often of the input data, and different probability distributions might behave differently. So let's define distribution-based equivalence classes as boundaries and try to find difficult distributions that might cause problems. So we then sat down and defined our equivalence classes. The first one was no algorithm should fail when we just input uniform data that's well behaved in the interval 0, 1. That's the most basic thing. We're interested in smoke testing, so basic properties should always be fulfilled. But then we thought about more difficult scenarios. For example, let's go to the classic boundary. So what happens in the area of max double? So let's take data close to that. Or what happens if we go to the lower boundary of machine precision and take data that's really, really close to 0? So maybe that triggers an underflow, whereas the very large data triggers overflows. Or let's just throw in all zeros. Then maybe something like a division fails, or a standard deviation cannot be calculated. What happens if our data is really badly skewed? So a lot of data is on one side and we have then a long tail to another side. Or even more extreme, if we have all data in a very small interval, except one single value, which is really, really far outside. Or when we have disjunctive training and test data. So what happens if we have data during testing that was never seen during training and is not even close to the data from training? And others. We then combined this equivalence class approach with combinatorial testing. And that is, we consider the combinatorial testing of the hyperparameters. So many machine learning algorithms are configurable. So for example, this is the configuration interface of a decision tree in Weka. And you can see there are many options. For example, the minimal number of objects in a tree leaf, or how the tree validates itself, stuff like that. And this affects which parts of the source code are covered. So to achieve a high coverage, prior research showed these hyperparameters must be considered. We use a relatively simple linear approach for this, where we vary one parameter and keep all others the same, because a grid search with this amount of parameters was not feasible. We then wanted to know, when we do this kind of smoke testing, can it help? Can it find bugs? We defined 22 smoke tests. You saw 7 of them earlier. And we implemented them for 19 different clustering algorithms and 53 classification algorithms. These algorithms are from the latest releases at that time, so this was now 1.5 years ago, of 3 state-of-the-art frameworks, so scikit-learn, Weka, and Apache Spark. We decided to use these frameworks because they all provide fairly mature machine learning libraries. And our assumption was, if we can find bugs in mature libraries, we probably also can find or prevent bugs during the development. So then these are really good smoke tests. When we ran these tests, the most important aspect we found was that very, very large values close to max double are well suited to uncover bugs. So for example, we found Stack Overflow or out-of-memory errors depended on how the Java virtual machine was configured for 7 Weka classifiers because a split in the decision trees was badly implemented and just led to an infinite recursion. We also found a memory error in the agglomerative cluster of scikit-learn that we could trigger with 5 instances that we threw in there, so a couple of kilobytes of data were sufficient to use up all your local memory. Weka also produced an illegal number of clusters for EM clustering because the estimation of how many clusters are required just failed when the data was too large. And there were more problems with max double. One of these bugs, so for one of the 7 Weka classifiers, was actually only found for one specific hyperparameter setting. So one flag needed to be activated, otherwise we wouldn't have found this one bug. The other tests were also effective. Not all of them, but we, for example, found also tests with zeros. So the nearest centroid classifier of scikit-learn then tried to compute a standard deviation, and that failed because of the division by 0. The naive Bayes implementations of scikit-learn, and there are multiple of them for different variants, all failed with an index out of bounds if all data just comes from one class. So there was an implicit assumption in there that all data has at least 2 classes. Usually not a problem, except for the naive Bayes classifier of scikit-learn. And Weka's Bayesian network just failed with an integer overflow if you have too many very small categories in your data. And again, there are more test results which you can find in our paper. We then wanted to know if developers care about this testing, because it's one thing for us as researchers to consider these bugs, it's another to actually help to improve the software and whether developers care about this. So we wrote up reports of our test failures and sent them to the developers via the mailing lists or issue trackers. So we sent them to scikit-learn via the GitHub issues, to Weka via the mailing list, and to Apache Spark via their Jira issue tracker. In scikit-learn, 4 bugs are already fixed, and for a 5th, the pull request acceptance is pending. One of the bugs was actually fixed within 24 hours, so this was really, really fast. So that was, for example, the memory error I mentioned earlier. The Weka developers acknowledge that all are valid bugs and this behavior that shouldn't occur, and they would merge patches, but they won't invest the effort themselves to maintain this library in this direction. And the Apache Spark developer said, yes, you found a bug here, but we don't deem it very important, so we won't fix it. From this study, we derived 2 key messages for researchers and software developers. First of all, simple tests also work. So define a simple smoke test suite to find low-hanging fruits of bugs. And second, do not forget the hyperparameters. Otherwise, you will miss parts of your source code during testing and likely also miss some bugs. Thank you for your attention. We discussed in this paper a smoke testing approach that can be a part of a larger and complex test process for machine learning software, and showed that this was effective at finding bugs in 3 major frameworks. If you're interested in our work, please consider our paper, but you can also listen to the Fuzzy Quality podcast of Adam Leon Smith, in which we also discussed our paper. Thank you for your attention, and looking forward to hearing from you in case you're interested in our work.